Hello! In this video, we are going to prove the following theorem. Suppose phi is a group isomorphism from a group G to a group G bar. Then G is abelian if and only if G bar is abelian. Now let's remind ourselves. Since phi is a group isomorphism, this means that phi is a bijective function from G to G bar. And phi preserves the group operation. More precisely, given any two elements A and B in G, we have that phi of A times B is equal to phi of A times phi of B. Now, before we prove this theorem, we are first going to prove a preliminary result. We're going to prove if A and B are any two elements of G, then A and B commute in G if and only if phi of A and phi of B commute in G bar. Now, we're trying to prove a statement containing if and only if. So to do that, we're going to prove if A and B commute, then phi of A and phi of B commute. And then we're going to prove if phi of A and phi of B commute, then A and B commute. Let's first prove the forward direction. We're going to prove if A and B commute, then phi of A and phi of B commute. And to do that, suppose A and B commute. Now, since A and B commute, this means AB is equal to BA. So when we send these guys into the function phi, their output values should be equal. So phi of AB is equal to phi of BA. But since phi preserves the group operation, phi of AB is equal to phi of A times phi of B, and phi of BA is equal to phi of B times phi of A. So this shows phi of A times phi of B is equal to phi of B times phi of A, so phi of A and phi of B commute. So this shows if A and B commute, then phi of A and phi of B commute. So this proves the forward direction. Now let's prove the converse. We're going to prove if phi of A and phi of B commute, then A and B commute. And to prove that direction, suppose phi of A and phi of B commute. Well, let's note, since phi preserves the group operation, the left-hand side must be equal to phi of AB. The right-hand side must be equal to phi of BA. So this tells us that phi of AB is equal to phi of BA. But phi is a bijective function. So in particular, we know that phi is injective. And since phi is injective, well, that tells us if we have any two output values of the function phi equal, then the input values must be equal. So this implies AB is equal to BA. So A and B commute. So this proves if phi of A and phi of B commute, then A and B commute. So we've proven the converse. And at this point, we've proven both directions of this statement. So this proves our preliminary result. So now let's get into proving the main theorem. Now again, we're trying to prove a statement containing if and only if. So to do that, we're going to prove if G is abelian, then G bar is abelian. And then we're going to prove if G bar is abelian, then G is abelian. So let's first prove the forward. We're going to prove if G is abelian, then G bar is abelian. And to do that, suppose G is abelian. Now, to prove G bar is abelian, we want to show that every pair of elements of G bar commute. So let's give ourselves two arbitrary elements of G bar. I'll call them A bar and B bar. Since phi is a bijective function, then in particular, we know that phi is surjective. And what that means is, if we have any element y in G bar, then there must exist an element x in G, such that phi of x is equal to y. So in that case, since A bar is an element of G bar, there must exist an element A in G, such that phi of A is equal to A bar. Similarly, since B bar is an element of G bar, there must exist an element B in G, such that phi of B is equal to B bar. Now, since G is abelian, A and B commute. So we have AB is equal to BA. But then, according to star, since A and B commute, it follows that phi of A and phi of B commute. But phi of A is equal to A bar, and phi of B is equal to B bar. So this is saying A bar, B bar is equal to B bar, A bar. So we have A bar times B bar is equal to B bar times A bar, or in other words, A bar and B bar commute. So we've shown if A bar and B bar are any two elements of G bar, then they commute. So that shows G bar is abelian. So we've shown if G is abelian, then G bar is abelian. So this proves the forward. Now let's prove the converse. We're going to prove if G bar is abelian, then G is abelian. To prove that, suppose G bar is abelian. The whole goal is to show G is abelian, which means we want to show that every pair of elements of G commute. And to do that, let's give ourselves two arbitrary elements of G. I'll call them A and B. Well then, if we send A and B into the function phi, we have that phi of A and phi of B are elements of G bar. But then, since G bar is abelian, phi of A and phi of B must commute. But then, according to star, since phi of A and phi of B commute, that implies A and B commute. So we see, given any two elements A and B in G, it follows that A and B commute. Therefore, G is abelian. So we've shown if G bar is abelian, then G is abelian. So this proves the converse. And at this point, we have proven both directions of this statement. So we've proven the theorem. So this completes the proof. And so yeah, that's pretty much it for this video.